Okay, we're going to have a bit of an examination of this particular plot. I'll give you some verbal descriptions of some of these methods here, particularly nearest neighbours, tree, discriminant analysis and support vector machines. I'm just going to discuss them with reference to the plot. I'm not going to go into them in any detail. We'll look at the naive Bayes classifier in a little bit of detail, and then we'll go into logistic regression feeding into a discussion about neural networks in quite a lot of detail. Okay, so we've got this plot here. And just before the break, I asked, what would be the simplest way you might predict the class of a new data point, which was somewhere in this blue group here. Okay, and the suggestion was to look at the nearest neighbour, or the k nearest neighbours, or the weighted k nearest neighbours. And yes, that would work well. Okay, for this particular data point. Okay, but what happens if you've got a new data point that's here with something like a nearest neighbours approach, a k nearest neighbours approach? Okay, let's play Jeopardy. The answer is hard classification. Okay, so k nearest neighbours is an example of a hard classification method. And when you have overlapping categories like this in the feature space, hard classification is a problem. You might not actually want to have one or the other. You might want to have some idea of the likelihood that it's in one class versus another. So you may want to stay away from a hard classifier. How do we get away from that? But I don't want to use a distribution at this stage. I'm a lazy person. I just want to do something simple that works. Maybe it involves a tree. How could I possibly get a soft classifier that doesn't use probabilities? Because they're ugly, they're a nuisance. I've got to check Wikipedia to see what the functional forms are. Don't want to do that. What's something else I could do?
You make a new.
Yep.
Could you make like a new sort of class that is some sort of capturing the ones that are in the
gray space between those two, like an extra class?
Yeah, you
that
could do
somehow combines. Yeah. It's like thinning.
Yep. So that's called bagging, right? So you group classes into a bag, chuck them into a bag, and then do some sort of tree-based clustering method. Okay. Another thing you might want to do is you might want to. It doesn't really work for this particular data set, but you might, if you had, say, a data point that was out here somewhere, you might think that it could be a high chance of being in the teal cluster versus the blue cluster. But if you just ignore one of the features, it's quite clear that it's really closer to the teal cluster, right? So that's called feature bagging, or it's the underlying principle behind something like random forests. So random forests are a way of generating tree-based classification rules that reduces the chance of overfitting and can give you probabilistic interpretations. And the way they work is they drop features. So you build a random forest where you randomly drop features out. In this case, where we only have two features, it's kind of hard to explain. But if you had a data set for the stability studies that Spiros was looking at, where the features are things like the voltage levels at certain buses and the input, the steady state power flow, say generation levels and load levels, and line currents and various other things like that. Your random forest would drop a bunch of those to build one tree, okay, and then drop a different bunch to get the second tree and build up a very large set of trees, a forest. Do the classification according to each of those trees separately, and then to do hard classification using the random forest, you take a vote of the class according to following the trees, all of the trees, and a plurality vote, so that's the most voted for label, tends to be a good way of doing the classification. Or if you wanted to do a probabilistic interpretation, you just take the frequencies, right, and that would give you a soft classification. Right, and there's no probability distributions. It's all tree-based. It all, you can explain it to a youngster, no trouble. Okay, so these things can work. So these tree-based classifiers, so decision trees, random forests, and within decision trees and random forests, there is a multitude of algorithms for training or identifying the decision trees. And the selection of these things can affect performance really quite dramatically. One of the big reasons we use forests rather than trees is that you get some sort of robustness in the result that you get by using these random forests, by having lots of different approaches and then combining them rather than just going with one approach. It's kind of a wisdom of the crowds idea maybe, but applied to decision trees. But it's a little bit unsatisfying in some ways because it's quite heuristic. But in terms of first things to do, bagging and random forests will get you a long way. So these are sometimes called ensemble methods as well, where you have an ensemble of trees with reduced feature space. Okay, right. So these two clusters here are particularly problematic. But let's just consider, say, how we might identify this cluster compared to the rest. What's another fairly straightforward way we might separate this cluster from the rest?
You could use some hard limits, like if y is less than 3 and x is less than -2.5. Sort of rectangle. Sorry.
Yep, that sort of thing would work. That would be, though, an example of a rule in a decision tree. But yeah, that sort of thing would work. What I was thinking about was actually something like a linear discriminant or discriminant analysis. The idea is to find a line that separates classes. So linear discriminant analysis, which it's been around for 100 years, is the particular problem of finding a line that will separate one class from another. And it's usually done pairwise. Okay, so you might find a set of linear discriminants that collectively can identify your classes. In the case where you can't completely separate them, you can apply a penalty function for linear discriminant analysis. It's usually a quadratic penalty. The idea is then rehashed in something like support vector machines. So SVM. How many of you have heard of SVM? Yeah, right, okay. So SVM is widely used because it works. The idea of SVM, the underlying approach is slightly different between discriminant analysis and SVM. Discriminant analysis takes orthogonal projections and blah, blah, blah. The support vector machines try to find two support vectors, two lines connecting that are parallel that touch on the different classes with maximum width between them. Okay, so for the case of trying to identify or classify the green compared to the rest, we might find a pair of support vectors that touch on, say, this point and run parallel this way. Okay, that maximizes the distance between those support vectors, okay, without having any of the two different classes encroach on the area between them as given by the support vectors. Up here we've got a bit of a problem though, because we can't find that clear distinction. Yep.
Actually, I have a rather philosophical question. Yeah. So, why should we think that the blue dots and the yellow dots that are overlapped are from different classes? Why?
Oh, that's the way we've measured the output. Yeah. So there's something about the output which tells us that they're different classes.
Because in terms of the features, the two features, they are...
Yeah, so are they actually functionally different?
Yeah.
Yeah, what's your application?
Mm.
Yeah, but your point's taken.
Yeah.
Why is it we're trying to discriminate between those two?
Exactly.
Yeah, that's a good question.
Any real-world application that something like this might happen?
Yeah, where you have, so in a lot of medical applications, you have observable things that are really close together, but there's some latent variables that you can't observe,
Yeah.
but reveal different classes. Yeah. So treatment of disease is a big one. Yeah. The human body being a highly non-linear system and having and complex system has some parallels to a power system, where the non-linearities in a power system's operation, particularly for the transient response to large disturbances, can lead us to a situation where something that looks like, say, a secure operating condition isn't secure. And it's not entirely clear why, just from simplistic analysis, and we need to do something a bit deeper to work out what's going on.
Doesn't that mean that we fundamentally lack the information to make the classification in the first place?
Yes, which is why we use soft classifiers, so that we can, rather than say, we don't know, we can say, well, the spot that's here, it's a little bit closer to the yellow, and under these certain assumptions around the distribution of features given a class, we might associate it with one class slightly more than another class. Okay, so we would associate it with the yellow class if it was in here slightly more than the teal class.
And then we're using these two metrics to kind of assign probabilities. In a way, there's also then the uncertainty to do with that probability because of the lack of information which is actually deciding the class.
Exactly.
And can we get at that or not?
Yep, we can.
Okay.
Yeah, you go down the Bayesian route again to handle that. Okay, so these are good questions. So you're getting into a deeper understanding of what we're trying to do and why we're trying to do it and what tools we have at our disposal. So I was just trying for this particular demonstration to highlight really reasons why things like hard classifiers that you get for support vector machines, linear discriminant analysis, tree bagging, random forests, k-means, why they have some limitations when you have these sort of confounding, overlapping classes in your feature space. Now, having said that, there are some tricks that things like support vector machines can apply. There's the classic example that you'll see demonstrated for support vector machines and also spectral classification methods, which I'm not going to touch now, where you have one class as a circle in the middle of your feature, your two-dimensional feature space, and then the second class is a ring around the outside. Okay, and what you're interested in doing is finding a way of partitioning these two. Now, in the two-dimensional space, you can't draw a line that partitions them. Like, it just doesn't exist, right? Yep.
In that case, could you redefine your two dimensions to something as radial and then apply the same boundary condition based on radius, for example?
Yep, that would be a spectral decomposition. Right, would do that automatically, or some sort of, more generally, some sort of transformation. Okay, so if you switched it to polar coordinates, then the magnitude from the midpoint would give you a way of clustering for sure.
With these transformations, I'm wondering if they would have to be strict to the three sets of coordinates that we're most comfortable with, or would they just be could use some completely obscure mathematical transformation which warps the space entirely to one where it's easy to split?
There's some good strong theory around this. It has to do with the replicating Hilbert space kernels that were mentioned by Anna. Basically, the set of valid kernels which are just transforms that you can use for something like a support vector machine to transform, this is the kernel trick I mentioned before, to transform your low dimension data into higher dimensions in order to separate it. There's certain properties that the kernels have to have for this to be mathematically sound. The main one is that they're symmetric, but there's other things to do with the area under the integral of the kernel has to add to 1 and various other things on the Jacobians, the second order conditions, and they have to be unimodal as well. So for the example that I was giving, where you have the data clustered in the middle and then a circle around, a simple thing to do would be to apply some sort of polynomial transformation, which, if you put this into 3 dimensions, lifts the center up. Okay, and then you can apply a hyperplane to cut that middle out and leave the ring at the lower level and the center at a higher level. Okay, so this is the kernel trick. It's a lifting mechanism where you take lower dimensionality data and raise it to a higher dimension in order to find a hyperplane that separates your data. Okay. The problem with doing that is if you start with high dimensionality data and then you're trying to lift it to even higher dimensions, you run into the curse of dimensionality, right? Where all of a sudden your tensors, your multi-dimensional arrays, you're making them of even greater dimension, and the computational power needed to analyze these things grows exponentially with the number of dimensions. Okay, so this is bad news. Computers keep getting faster, but the problems we try to tackle are growing quicker than the rate at which we're improving computing power. Right.
But isn't the lifted object necessarily sparse? How do you...
It can be, but now we're getting into details, right? So now you need to know about this.
Yeah, I was talking about sparsity of the lifted object.
Yep.
So certainly that's a good trick. The problem is that then you have a much bigger space, but in reality you were already extrapolating, so you may have noise that sort of obscure what you want to do in the lifted space. But in fact, you are coming with an object that is sparse in a higher dimension.
Yep.
So there might be tricks that one could may be able to use to reduce that dimensionality.
That's exactly right. Right. So then you might lift and then apply something like principal component analysis to work out which are the most valuable dimensions to be looking at, and just drop the rest. Then do your computation.
I had a comment, just a thought on this classification and the hard classification. Just my background from system identification, classic methods for recursive model fitting and so on. One has this way of approaching that data with prejudice, which is your model structure, and then you use your prejudice to try and fit the best you can parameters into that structure. So isn't classification something like that, where you somehow the clusters are a construction? I mean, they're not there. It's just a way of dealing with these clusters are not naturally arising. They are only in our heads. So that the hard classification I'm thinking is kind of a problem that we pose to ourselves, because we insisted on something that looked like, in some cases, there's no way of separating those two clusters into one. But if we insist in having that particular structure to fit things in, might not be always the case. Is that?
When dealing with clustering, yes. But here we're dealing with classification, where we have the training data. So we have the Y labels, and they have meaning, and they're important to us. So in that case, it's not something in our mind. It is a real thing. Okay, it's a stability flag on a power system, or it's some sort of warning flag on some sort of system that you're looking at, right? So you have those labels that you're training against, and they do have meaning. In the clustering case, though, your point stands for sure. Yep. The fact that we can't separate these two clusters, though, motivates things like naive Bayes classifier. Okay. So that's what I'll jump onto now. Okay. So. Yeah, there's another question.
But instead of just using one classification technique, can you use a multiple?
Absolutely.
And then wrap another machine learning wrapper around that to decide which ones are best under whatever the circumstances might be? Because that's always been my approach to my limited work with clustering, is that you don't know whether your cluster's right or wrong. Mm-hmm. But if all of your techniques point to Rome, well, then that's probably the way to go to Rome. Exactly. Like if you get a consensus, you can. It's not perfect, but all of a sudden now you have more confidence.
Absolutely.
That this is the way to proceed.
Yeah. So I made reference to something like that when I mentioned ensembles of trees resulting in forests, and use voting mechanisms to determine your hard clusters, or you take frequencies to get soft clustering. Ensemble methods generally are the cutting edge of doing these things. I won't talk about it here, but I've forgotten his name. He's over at the University of Melbourne, at Monash University. There's people from Monash here. There's a time series clustering guru over there, whose name... No. There's a younger fellow than that. Maybe he's not the guru. But anyway, the problem of time series classification is hard. It's really hard, and the methods that are performing exceptionally well at the moment are these ensemble methods, and they're ensembles of 15 different network architectures, neural network architectures that each have 10 instantiations based on different subsets of the training data, and then you take the average or the vote across them. And that's what seems to be working well. These people, of course, have access to immense computing power, and you might have a laptop. And you may not need to be so rigorous in your study. You may be able to get a long way with something a bit smaller in terms of the model architecture. And the other issue with using big ensemble methods, beyond just the fact that having a lot of members of your ensemble takes a long time to train, is as we get larger and larger data sets that we're trying to deal with, it just becomes intractable. Right? So yes, they work very, very well. Ensemble methods are definitely a thing to investigate, but at the same time, it's good to know why certain things work better than others within your ensemble to help you select what's in your set of methods in the ensemble. Yeah. Which is what I'll go into a bit more detail here. Okay. So the naive Bayes classifier, right? It's pretty straightforward, really. The idea is we have this training data, we have input and output observations, and we know Bayes' rule because we had it drilled into us from high school. That effectively tells us classes given observations given the training data, okay? Right, based on the training data. So we use Bayes' rule. We can use the conditional probability of seeing a particular set of inputs given outputs to train, applying it through the probabilities, the marginal probability of the different classes arising in our training data gives us the likelihood of having a particular outcome given our inputs. Okay, this thing becomes a normalization constant. Okay, now the catch is that when we repeatedly apply Bayes' rule to training data, we have to take into, if we're doing this rigorously, we have to take into account the fact that input data is correlated. Okay, we can't just discount that. So the input data is correlated, and that means that expressing this probability, that's a vector x, right? So rolling this out, right, would involve taking the probability of x given the class and the previous observations. Okay, so for one observation it's fine. For two observations you've got to take it. In the second one you've got to take into account the observation of the first one. For the fifth one you've got to take into account the last four as well. And these conditional probabilities grow and become really difficult computationally and numerically to manage. That would be a Bayes classifier. A naive Bayes classifier says, forget it. Those conditional dependencies on in the input data, we can assume that within a class, they're independent. Okay, let's make this assumption. It'll make things a lot easier for us. So instead of rolling out a series of probabilities that are conditional on past observations, we just say, well, the probability of seeing X, given it's in a particular class, is this thing, and we'll approximate the true probability with the dependent relationships using this, this conditional independence approximation. And that makes this computation remarkably easy. We get a form that looks like this, where we have our prior, and this is the probability of the classes arising in the data when you're not looking at the individual events, so it's just a frequency, times the probability of seeing data associated with particular, conditional on it being in a particular class or associated with a particular class. We don't have to worry about the relationships between the data within the classes. We just drop it, forget it, okay? To turn this into this is a proportional to rather than a probability. To turn it into a proper probability, we have to normalize. We have to get this P of X. But to normalize, we just take the sum of this element for all classes. Yes, for a small number of classes, that's not a hard problem. And that returns our probability of a particular data object being in a class given all the data that we've seen. Okay, under that conditional independent assumption. And as I say here, despite its very tenuous assumptions, it does remarkably well, the naive Bayes classifier. Okay, so this is one of the first go-to things you could try when you're trying to do some probabilistic classification. It'll get you a long way. It might solve a problem that you have in hand. But if you want to do something more general, that takes into account, in some way takes into account the relationship between the data within the samples, so no longer relaxing your independence assumptions to conditional independence, but actually taking them into account, we need to use some more rigorous statistical methods. And the workhorse of these methods are what are called linear classifiers. Okay. So I mentioned linear regression earlier, and the class of linear classifiers is related to the idea of linear regression. It's built around a score. Okay, so a score function, which is a linear function of weights which you're training, and the input data. Okay, so in regression problems, this score is actually your prediction. And the idea is to minimize the squared, well, the standard idea under least squares regression is to minimize the square of the distance between the true observed output values and the predictions under your linear model. And for regression, we have the nice results that we can use the least squared estimator, which is, the x prime x, xy thing, which has nice properties and works and is analytically tractable, and you can solve it without actually inverting the matrix using the LU decomposition and blah, blah, blah. Right? It works. But for classifiers, we don't have that. We can't do that because the score doesn't help us. It doesn't actually classify for us. It just gives us a score. It's like an affinity to a particular class versus another class. But in general, linear classifiers can be used as hard classification methods. You take your linear score and you assign your unobserved output label, given its input data, given its features, to the class which has the highest score. And that gives you a fairly simple classifier based on a linear scoring rule. But that S, as I said, it's like some sort of affinity or score. It's not a probability. Okay. The other thing to note is, just like in linear regression, in linear classification, you can take all sorts of transforms of the raw data X. Again, the kernel trick applies here. Okay, but you don't need to just use the thing that's used regularly in support vector machines. You can apply all sorts of transformations to your independent data, your input data. You can apply very funky things like dummy variables based on thresholds, interaction terms where you multiply or otherwise combine input data. You can use higher order polynomials, logarithmic transforms, whatever you want to do, really, to generate your features. And then just the weighted combination of those features will give you your score. As long as you have this linear form, so weights times features, you have a linear classifier. Any transforms that you do to the input data, that's not part of the classifier as such, that's just something that you do to generate features. Right. So feature selection in these sorts of settings is something that you really have to toy around with. Automated methods for feature selection are difficult to come up with simply because of the combinatorial explosion of different features you could generate from any set of raw data. By the same token, you don't want to overfit. So you don't want to generate lots and lots of features, fit your model, get a really accurate classifier within your training data set, and then find it does rubbish on a test set because you've overfit. And there are methods for penalising overfitting based on the number of features that you include in your linear classifying score. Okay. These are called regularization methods, and they're basically penalties for putting in too many terms and trying to make your within sample accuracy too great. You can avoid that by just not including too many features. But when you're trying to automate these things, regularization helps you automate things. Okay, I was going to talk here about the kernel trick, but we've already mentioned that, so I can skip over. And jump to logistic regression. So I learned logistic regression when I was training as an econometrician. I knew nothing of information theory. This was last millennium, so neural networks were a thing that no one really used. And this was explained to me in terms of what's called a latent class allocation framework for discrete choice in like product selection problems. I've since educated myself further and seen the deep connections that this has with information theory, which I'm going to go through here because I found it really interesting when I learned it for myself. So we'll start with binary logistic regression, but we'll do an example of a multinomial or multilinear logistic regression in a sec. Logistic regression, the idea is that you're trying to find the weights that best fit this particular predictor or classifier for y. Okay, so if this is bigger than 0, this linear combination of weights and input data is bigger than 0, we have the class membership for the first class being equal to 1 and 0, otherwise it's part of the second class. It's binary classification, right? So there's only two classes. Where we assume that the error term is distributed with the logistic distribution. Okay, so this is a really statsy kind of way of approaching this problem. You assume some sort of distribution, you fit a model that minimizes the loss or the error in your predictions, subject to that assumption around the distribution being true. Okay, all of undergraduate statistics pretty well plows this same furrow, usually where the distribution is normal, and everything that you do is to try and transform input data in a way that gets your predictor to be accurate and have normally distributed errors. Right, that's first, second, and probably third year stats explained in 2 sentences. Logistic regression, same thing, but logistic distribution for the error term. How exactly it does that is it makes use of the odds of y happening for different x, y, and then takes the log of those odds. So this gives you a representation of the log odds of the two different outcomes, x and y. You go through some algebra and you end up with a nice, neat functional form that looks like this, which hopefully you recognise as a sigmoid function. Okay, where our linear score appears down here. Okay, so that's the score, the linear score that we had on the previous slide is now the exponent in the denominator there. As that score goes from a very negative number towards 0, this value goes from 0 and slowly and then increasingly quickly to 1, to a half, because we've got 1 half, 1 plus 1 under 1. And then as you go into positive values, it goes up towards 1. So this thing's always bounded between 0 and 1, and it gives us a way of mapping from a linear score from infinity to infinity onto this space of 0 to 1. This y hat is a probability that y is in the particular class k. Okay, we interpret this as a probability. The value is between 0 and 1. We can interpret it as a probability under this assumption that the errors are distributed logistically, and this gives us a nice soft classifier. Okay. Now this idea has been around for a long time. It's really, really useful, and it scales immensely because of the use of the linear scoring rule in there. Just to go off on a bit of a tangent, neural networks are great for a lot of tasks. They're not great when you have small amounts of data because you have so many weights and biases and things that you need to train. So you just can't train them because you don't have enough information to train sensibly. But they're also not great when you have really, really large data sets, because the computational task of updating the weights over that really large data set becomes prohibitive. Okay, so in the first case, we have small amounts of data, a Bayesian framework's suggested. In the second case, where you have these exceptionally large data sets, we end up falling back to lower and lower complexity neural network architectures. And the lowest complexity neural network architecture is the one with one node, okay, and no hidden layers. and a sigmoid output function given by this thing. It's logistic regression. It's the thing that becomes tractable as your data sets get very, very large, is this thing. So the development of neural networks over time started with this, and then adding mixtures of these things, throwing in biases, adding hidden layers for latent variables you couldn't observe, finding new ways of updating weights and the thresholds and biases that improve the performance, adding recurrence, adding other interesting ways of maintaining stateful information into your neural net. But this all becomes impossible to use when you're trying to train too many of the parameters in the neural net, given the size of your input data. So you roll back the size of the architecture, you eventually end up back where we all started, or where this started about 80 years ago. Okay, so logistic distribution, you're familiar with the sigmoid, I'm hoping. This is just for one dimension, but as the weight increases, we can see that the steepness or the sharpness of this logistic function grows, and as the weight gets very large, it becomes something like a step function or a Heaviside function. Okay. In this case, the probability given the input data for this one-dimensional case, the probability that you're in the first class is given by the distance from the axis to the curve, and the probability that you're in the second class is the remaining distance. For multinomial problems, it's not so easy to show, but the idea is that the sum of those distances up to the curve all add up to 1. Okay. So training this thing. For linear regression, training is not a problem because you have an analytic solution. You just have to run the numerical computation to get your least squares error or weighted least squares error, or two-stage least squares regressor. Right? These things are analytically closed form. For logistic regression, we don't have closed form solution, so we have to use a search method within a maximum likelihood framework. Okay, maximum likelihood. So we're going to maximize the probability that our class labels are correct in our training data, given our inputs. Right. It's all starting to get a bit confusing. Am I losing people? I think so. I can see people looking all around the place, but that's okay, because what is going on here is the next question that I'm going to ask. What's actually going on? Okay, I approached that to start with from a very statsy direction. We assumed logistic distributions. We had a linear classifier to keep it tractable. I threw up the term maximum likelihood estimation. The eyes glazed over. People stopped listening. Phones were being inspected. So what's really going on here is something more general. This is an example of a more general way of training classifiers. Okay, so as I say here, sigmoid functions like logistic function, the hyperbolic tan, also another one, form a very important part of many neural network architectures. And what we're going to do next, and we're going to do some coding, is to have a look at the connections between logistic regression and various classifier loss functions used more generally in machine learning. Okay, so we're going to get to logistic regression from a different direction. Okay, here's our artificial neuron. We have inputs, weights, a propagation function, which is a sum, in this case, a bias that we're applying to it, an activation function, which in our case is the logistic sigmoid, and an output, which is a probability of being in a particular class. We could squash that and make it into a hard classification if we wanted to, so you'd have to add another layer. But for the time being, let's say Y is a probability of class membership. Okay, this is one neuron, but you could frame it in terms of a neural network architecture. Okay, and you can see that these things are the same. They're not similar. They're not kind of like each other. They are exactly the same. In this particular case, we have the linear score, so linear combination sum, and the activation function being the logistic function. They are exactly the same. How do we train that in the machine learning way of approaching these things? Well, what we do is we would assume a loss function that helps us choose or select the parameters of the classifier so that the output y hat is as close as possible to the correct output y, okay? And the loss function tells us how close is close. So the loss function really, as I'm saying, it should prefer that we get it right. And this is a what's called a conditional maximum likelihood problem, where we're choosing the parameters, the weights and the biases, that maximise the log probability of the true y labels in the training data given the observations x. Okay, based on this, if we're using conditional maximum likelihood and log probability that we've got things right, we get what's called the cross-entropy loss function. Okay, cross-entropy loss functions are really useful. They work very well. They're quite general, and we'll see how they are linked. So let's see how we get to that. So we want to maximise the probability of having the correct label given the training data. So this is a conditional probability, py given inputs x. Stepping back to the Bernoulli distribution, which I mentioned earlier, there's only two outcomes in the binary classification case, or 1 or a 0. So this probability y given x is a Bernoulli distribution given by that functional form there, where y is our probability and y hat is our probability, and y is the number of class labels that appear in the training data. Okay, so that's that's the class label. So in this case, this is in the case of this being 1, that's 0, or if it's 0, that's 1. Taking logs of both sides, because that's always a handy thing to do when you're dealing with ratios, gives us this this form here of the log likelihood. Okay, and then flipping the sign around, this would be a maximisation problem. We're trying to maximise the log likelihood, and flipping the sign around gives us the cross entropy loss function. Okay, now why is it called cross entropy? How many of you have seen Shannon entropy in communications theory? Handful of you? Yeah. This term here, this cross entropy function, is related to the Shannon entropy that you have on a communication channel. The cross entropy is telling you how much information you need to communicate in order to model one distribution in terms of a different distribution, to change it into the correct target distribution. In the example, we're not going to have time to go through, or do we start on it and then come back to it? We might start on it and then continue with it later. So I'm going, in the example code that you've got there, if you want to fire up your laptops, we're going to have a look at how the cross entropy is used to measure the performance of a classifier in general. Okay? And we're not going to assume a classifier. We're going to assume the output of a classifier and play around with the output of the classifier in order to see how the cross entropy works, and also make explicit that link between the Shannon entropy, the cross entropy, and another thing called the KL divergence, the Kullback-Leibler divergence, which is like the marginal cross entropy, the additional bit of entropy you need to inform the difference in probability distributions. Open up cross entropy.py. So here if you run the code, the first thing that pops up is a pair of bar charts. Okay. What I want you to think of this as being is the top one being our target distribution of classes from the data, and the bottom one being the class allocation frequencies under a not particularly well-performing classifier. We're going to use this concept from information theory to measure the difference between these two. We'll measure the amount of surprise that we might have in one, and then the difference between the two of them, using these measures which we call cross entropy and KL divergence. So I want you to inspect the code as well, not just run it. So in the code, we define these three terms, the entropy, cross entropy, and KL divergence. The cross entropy is the thing that we're using to, you regularly use to train machine learning algorithms. Sometimes you might see people using the KL divergence. There's no problem with this because the cross entropy is the entropy plus the KL divergence of a distribution. So the KL divergence just removes a constant. Things working? It's working? Yeah.
What I found with your code though is I have to add interactive mode on, or else it wouldn't calculate anything after the first plot.
That may be the case. Yep. Yeah, because I was doing this through through the command line rather than through what are you using, Spider or?
Yeah, because I'm running through the command line, just going pyplot.ion at the very top, and
Mhm.
the little buttons all the way through.
What is it? IO?
.ion, and then brackets open and close.
Thank you.
Plot it and then actually get.
It'll actually give it. Yep. So there is also an input call in there, making you go and look at what's going on in the code. That was the idea. Why is that not finishing? What do they say? A feature, not a bug. Okay, so if you execute that, what you see is that the I haven't changed the actual terms on the outputs. They're all H is what we usually use to represent the entropy, and I should have changed that for the various outputs, but I've omitted to do that. Sorry about that. You can tell which is which by the arguments of the function, though. Well, almost. The first two are going to be the cross entropy. The second two are the KL divergence. The third pair are the cross entropy of the probability distributions on themselves. And the last ones are the entropies themselves. And what you see is that the cross entropy of a distribution on itself is its entropy. But more importantly, the key thing here is to see that the entropy, the information content or the surprise element of the distribution is plus its KL divergence gives you the cross entropy between the two, plus the KL divergence between two distributions gives you the cross entropy of the two distributions. So all I'm trying to get you to understand there is that if you see KL divergence and cross entropy, you're trying to maximize or minimize the negative of as a loss function.